Let's take a closer look at a small segment of the transmission line. As we mentioned earlier, a transmission line must have a live wire and a ground, and its structure is uniform throughout. When the structure is uniform, we can assume that a line is composed of countless small segments. Our goal is to determine the relationship between the line and the signal it carries. We'll use the distributed circuit model, or RLGC model, which takes into account the losses and self-inductance on a non-ideal line. There are dielectric losses between the live wire and ground, and there are capacitive effects in between as well. To learn about different types of transmission lines, we can refer to textbooks on electromagnetism or microwave engineering. Understanding their characteristics requires determining the parameters of different types of transmission lines through electromagnetic field theory. RLGC is one of the electrical parameters used to describe the line characteristics. These parameters represent the resistance, inductance, conductance, and capacitance per unit length in the line's distributed model. These parameters are directly related to the line's geometry and the material used to manufacture it. And here we see R times delta X, where R is the resistance per unit length. When we multiply it by delta X, we can determine the resistance of this small piece of line. The same is true for the L, G, and C parameters multiplied by delta X. To analyze a transmission line, we begin by cutting a small piece out of it for discussion. We specify that the starting point of the cut is at position X on the left, and the ending point is X plus delta X on the right. Assuming that the signal is transmitting from left to right, position X is the input and X plus delta X is the output of this small segment. At position X, we denote the current flowing into it as I of x, t, and the voltage appearing here as V of x, t. From here on, we'll discuss both voltage and current as sinusoidal waves and how they propagate on the transmission line. Thus, we sometimes refer to them as voltage waves and current waves. We can see that voltage and current waves are not only related to time t, but also to their position x on the line. Our goal is to solve for the voltage wave V x, t and the current wave I x, t. We will use this model in the next videos to find the relationship between voltage and current waves on an infinite length and lossless transmission line. Using such a model to analyze the line is a matter of circuitry. We don't see the electric and magnetic fields in it because their effects are already included in the RLGC parameters. The difference from a typical circuit analysis is that we are analyzing not only time-dependent, but also position-dependent voltage and current waves. Additionally, we are looking at a line as a circuit component, not as an ideal wire. Now the problem is how to find the voltage wave and the current wave. See you in the next video.